see, the technology is also making it possible for you and me to talk.
Yes, that's right. I'm grateful. So we'll tolerate the delay.
No problem at all.
Okay.
Absolutely no problem.
So, fine. Okay. So I will complete in 5 minutes.
No problem.
So friends, we have now assembled for the post-launch session, and this will be Professor B.B. Deo Memorial Talk by Professor Daya Shankar Kulshreshtha from University of Delhi. So a few words about both of them. Professor Deo, as you all know, it was also narrated in the morning session, is basically the creator of this institution called Odisha Physical Society, along with his like-minded people. That started in 1971. So it's already, as somebody said, it's nearly 51 years. So we are more or less celebrating the Golden Jubilee celebration of creation of Odisha Physical Society. And Professor Deo, in fact, will be remembered in the annals of educational history and physics history of the state because of 3 reasons, as I think. One is that he is actually the creator of computer literature in the whole of the state of Odisha. Because the computer that he got from UGC in 1971 to the physics department of Utkal University was the only computer, was not only the first, but the only computer available in the state of Odisha, and everybody used it, from scientists from as far away as Regional Engineering College Raulkela to Paradeep Port Trust to Electricity Board. Everybody, in fact, used that for their purposes, and all educational institutions were allowed to use it free of cost. That's number 1. Number 2, he also started this Odisha Physical Society as an institution builder. And number 3, he also brought modern research in physics into the state of Odisha, because there was nothing. So because of 3 reasons, I think he will always be remembered. And he is unique in this sense that he is perhaps one of the very few scientists in the state, in the country, who actually worked with equal quality in condensed matter physics as well as high energy physics, which is also called particle physics. So he had PhD students in both of them. In fact, Professor Behra, the memorial talk that you heard in the morning session, was his PhD student in IIT Kanpur. And he had many PhD students also in high energy physics. So and he also worked on ultrasonics, etc. Not only that, he was a theoretical physicist, obviously, but he had also a very, a very intuitive knack for the experimental physics. He worked on ultrasonics, he worked on various other kinds of instruments in Kanpur IIT also. So that way he is also unique. So it's very fitting that we actually commemorate his memory in the form of a memorial talk in the Odisha Physical Society. And Professor Kulshreshtha, who is going to give the Professor B.B. Deo Memorial Talk this afternoon, is from University of Delhi. He is very well known, particularly in the fields of supersymmetry, superstrings, and supergravity. So all the supers actually qualify his personality also. So he actually did his MSc from GIET University, Gwalior. He is in fact did extremely nice work of high quality in these areas, and he spent 5 years position in Kaiserslautern University in Germany, and he had a permanent position in University of Delhi, and he has published lots of papers. So we are in fact greatly indebted to Professor Kulshreshtha that he agreed instantly to actually give this talk in memory of Professor B.B. Deo. With these few words, I now request Professor Kulshreshtha to start his talk. Professor Kulshreshtha, please.
Oh, thank you. Thank you, Lambodharji. Thank you so much for your very, very kind words. And I must not forget to express my thanks to Professor Lambodharji, Professor Durga Prasadji, and all the distinguished organizers of this prestigious event, the convention of Odisha Physical Society, and we just now heard from Professor Lambodhar Prasad Singh, an old friend of mine, a very, very Vidwan person. Odisha has Odisha is fortunate to have lots of people with lot of wisdom. See? And my friends, Damodar-ji, Durga Prasad-ji, and moreover, I feel highly privileged and honored to be able to give this talk, Professor B.V. Dev Memorial Lecture, and I must say that I was very fortunate that I got a chance to meet Professor Dev a couple of times at Utkal University itself in Bhubaneswar, and whenever I would go to his office, once he joined us at dinner also in the university along with the faculty. He was a very modest person, very humble person, down to earth, and a very, very inspiring personality, very affectionate nature. I would call him a person full of affection for younger people. So that is how I would summarize it. I did not get a chance to work with him, but I believe that my colleague and friend Professor Lakshmidhar Maharana worked with him, and I have heard so many praises about him. So I pay my respect to Professor B.V. Dev through my talk. With that, then I come. With that, then I come to my physics talk, and the topic that I have chosen. Just 1 minute. Could I? Could someone help me make it full screen? Okay. So let me come back to my physics topic. I have chosen the topic for my talk today as quantum gravity, and this is one of the very fundamental questions in physics at the moment, which people are trying to understand from various angles, from various points of view. And I would try to convey my thoughts on my understanding of this topic, how we could proceed. My talk is primarily intended for the younger people and for the curious minds. So you see, the universe was born ये पूरा फुल स्क्रीन करना चाहता हूँ. Okay. All right. But I'm sorry for the interruption. I was trying to make it full screen. Actually, I could not see how to do it. So, all right. Let me stay with this. Hello. Yes. Yes. Wait a minute. On my screen, right corner is 3 dots. Yes. Okay. Yes. Okay. I see. I see. And I now just one more minute, please. I have got this. It says full screen. Words in the memory of Professor B.V. Deo, I come back to my physics topic, which I have chosen as quantum gravity. So, you see, the universe was born something like 13.7 billion years ago, and all the fundamental laws of nature, all the fundamental laws of physics, they were also born right at that moment. And we are trying to understand them now. So, we have two fundamental theories at the moment in our hands. One of them is quantum theory, and the other one is general relativity. And both of these theories have been tested extremely accurately up to several digits. So, you see, in quantum theory explains the physics of microcosmos, the physics of the universe inside the atom. And you see, a special theory of relativity gives us the possibility, it tells us the equivalence of mass and energy. And in quantum mechanics, we have the possibility of creating energy out of vacuum, which is not empty, but is a boiling soup of particles being created and destroyed. And this very property of quantum mechanics actually makes it possible to marry special relativity with quantum mechanics. As a result, what we get is a very beautiful theory, the relativistically invariant quantum gauge field theory. This is very beautifully summarized in the so-called standard model of particle physics. And it describes the quantization of three fundamental forces of nature: the strong nuclear force, the weak nuclear force, and the electromagnetic force. And this model has been tested extremely well up to several digits. Most of its predictions have come out to be true, have been tested experimentally. And what is the spectrum particle content of this model is we have 6 quarks and 6 leptons. These are the 12 matter particles. So up quark, down quark, strange quark, and charm quark, beauty, and top quark. So these 6 quarks. And we have 6 leptons: electrons, muon, tauon, and 3 neutrinos: electronic neutrino, muonic neutrino, and tauonic neutrino. These are the 12 fundamental matter particles, the constituents of matter that we have in our universe. Apart from this, we have the mediators of these fundamental forces of nature, namely a photon for the electromagnetic interaction, 8 gluons for the strong nuclear force, quantum chromodynamics, and W plus, W minus, and G0 for the electroweak theory. So these are the intermediate bosons, gauge bosons, that mediate the fundamental forces of nature. In addition to that, we have one more unique Higgs particle, which is a scalar Higgs. As we all know, it was popularly called as the God particle. So that completes the contents of the standard model, and it's a very extremely successful theory. Now let us have a look at the theory of relativity, which is general theory of relativity, which is a classical theory of gravity. This theory is also extremely well tested experimentally and is one of the beautiful theories of nature. Now, there is one very special peculiarity about this particular theory and its experimental verification that many of them might not be aware of that. The general relativity was born in the year 1915 at the hands of people like Albert Einstein and David Hilbert. And this theory was experimentally verified 70 years before it was born. So in the year 1845, there was a French astronomer by the name Leverrier. So Leverrier was able to measure accurately the advance of perihelion of Mercury per century, and it turned out to 43 arc seconds per century. And you make a calculation in your general relativity, and you will get the same answer, 43 arc seconds per century. So you see what happens is, let me just say a few lines about advance of perihelion for younger people. When the distance between our Earth and Sun is smallest, then that particular position is the perihelion of Earth. So Earth, for example, takes 365 days to make one revolution around Sun. Now, when it comes back after 365 days, its major axis has got rotated by a small angle, which is called as the advance of perihelion. Now, Mercury is a smaller object and much closer to Sun, and it with more eccentricity, so it makes several revolutions. It makes 88 days in the year instead of 365. So it makes one revolution around Sun in 88 days. So here it's an ideal object for measuring the advance of perihelion. And so theory of relativity makes the prediction, and Leverrier, the French astronomer, also measured it in 1845, and the two tally exactly perfectly well. So this is the first experimental verification of general relativity. Apart from this, in the last 10 years, there have been landmark things that we have come across. The gravitational wave detection at LIGO. You see, if you consider any two compact objects like neutron stars or black holes, when they make a binary system, you see, then eventually they merge into one. And in the process, they emit gravitational radiation, which is called as the gravitational waves. And it was reported, I think, it's less than one decade. So very accurate measurement of this gravitational wave detection. And then there is a whole lot of activity like mushrooms, theoretical work, experimental work from various angles. People are looking at this gravitational waves. Okay. Well, apart from this, other landmark things, the construction of the image of a black hole. A supermassive black hole sitting at the center of a galaxy called as M87. It's a very distant galaxy from our Milky Way galaxy. And this guy, the supermassive black hole sitting there, actually is a heavyweight champion of massive black holes or supermassive black holes, because it's I think 6.5 billion times heavier than the solar mass, and it's spread across 40 billion kilometers in the space, and so it's larger than the size of our entire solar system, you see. And this guy, so the construction of the image of this supermassive black hole through our Event Horizon Telescope, which makes use of an array of 8 telescopes spread across the world, spread across our Mother Earth. And it's a very beautiful construction of the image of this black hole, very inspiring. It has motivated lots of younger people from all fields. And then the most recent and super test of general relativity is through in the year 2020. These three guys, Roger Penrose, Reinhard Genzel, and this woman physicist, Andrea Ghez, they shared the Nobel Prize in Physics for 2020. It is for the theoretical discovery by Penrose and others, the theoretical calculations, and this experimental work by Gerhardt and by Andrea Ghez. That so you see, apart from this, in our own Milky Way galaxy also there is a supermassive black hole sitting at the center of our galaxy, and that particular location is called as Sagittarius A star or SGR A star. Now, because it is a supermassive object, so hundreds and thousands of objects revolve around it. Now, these experimentalists, Andreas Ghez and Raynald, Andreas Ghez in particular chose a particular star called as S2 or SO2, which revolves around this supermassive black hole sitting at Sagittarius A star in our own galaxy. And this star takes 16 years or so for one revolution around this supermassive black hole. Now, this brave soul, Andreas Ghez, the fourth woman physicist to win a Nobel in physics. So far, only the fourth one, unfortunately. I wish half of them should go to them. And she was able to measure very accurately the advance of perihelion, which I just explained, for this system of Sagittarius A star and this revolving star S2. And you see, this experimental measurement, which took 16 years, she was tracking this object for 16 years continuously, you see. So the good work, it needs dedication over a period of time. And it tallies exactly well, perfectly well with the theoretical calculations. So it's amazing, wonderful, great. So, so much is enough to tell us about general relativity. Well, then some younger minds and curious minds, they might start wondering if our general relativity is so beautiful, so successful, why do you look for quantum gravity after all? And that's a good question, why not? So now let me tell you some limitations of general relativity. What happens that there are several situations where general relativity breaks down or it does not yield any further new result that we would like to have. So there is an important question of singularities, you see. Black hole is a very well-known space-time singularity. And apart from that, we all know about the Big Bang. So what happens? Big Bang is a very well-known singularity. So universe was what, 13.7 billion years ago. So let me run the universe backwards in time, like running a movie backwards in time. Then if you could possibly do it, you would hit upon that singularity which is called the Big Bang, from where the universe originated, you see. Now, Big Bang is a very well-known singularity. Now, general relativity explains physics perfectly well, almost up to the Big Bang, but not quite up to Big Bang. It stops, it breaks down a little bit before that. This I will explain how. So, this is how the general relativity breaks down here. So now, let us look for the simplest kind of singularity. Let me explain a very first-year example. Let me consider our Mother Earth. Let me throw a particle from the surface of Earth. Let me calculate. It will fall back on our Earth. Now I increase the velocity. It will again fall back on Earth. But then the initial velocity just becomes equal to the escape velocity of Earth. Then what happens? This particle goes out of the Earth's gravitational field and doesn't come back. All right. Now, this escape velocity is given by a very simple formula, square root of 2mg by r. Now, so let me keep the mass of my Earth fixed and let me squeeze it. Let me reduce the radius. So, I reduce it, keeping the mass fixed. And then I can squeeze my Earth into a tiny spherical ball of the radius of the order of 8.43 millimeters. Please note, 8.43 millimeters, I have squeezed my Earth, and then at that point of time, my Earth becomes a black hole. Why? How? Because now the escape velocity of Earth at this point becomes identically equal to the velocity of light, or the some universal constant velocity, if you like, photons to have mass. Doesn't matter. So there would always be some universal constant velocity which you cannot cross. So at that point of time, so what it implies to us, even if I throw out a photon from my Earth, surface of the Earth, it will fall back on Earth. That means it has become a black hole. So nothing can escape a black hole. Well, in more general language, in more general terms, what we say is that we introduce a hypothetical imaginary idea of a hypothetical imaginary unidirectional surface around a black hole. We call it event horizon. So it's unidirectional. Things can go inside but cannot come out. And so this actually, you can, without going into details, you can take it to be equal to the Schwarzschild radius. So Earth then became a black hole. That radius, 8.43 millimeter, is actually the Schwarzschild radius of Earth. If I do the same calculation for our Sun, then this would be something like 3 kilometers. Then the Sun would become a black hole by the same calculation. Simple. Now, what is so special about black hole? As I said, that black hole represents the well-known space-time singularities in nature. So this is a singularity of nature that we have arrived at, we have reached. Now, let me give another simple calculation. Just calculate the potential energy due to a mass sitting at, let us say, at some origin m. So the potential energy would be minus gm divided by modulus of x. Now you make this calculation, take x equal to 1, 2, 10. Once I tried it while traveling in a train, and I found that after a few points, my paper was no longer enough, because you have to make several points. So what happens? Now, this is one thing. And if you increase the mass, m here, so heavier the mass, the potential well becomes deeper and deeper. So the potential energy curve due to this mass m, even just simple one-dimensional plot, it would be a well like this, and you increase the mass, Earth's mass of Earth, mass of Sun, mass of a black hole, supermassive. The potential energy well would go deeper and deeper and deeper, and therefore people make a philosophical statement that there are even singularities even inside the black hole, because you see, event horizon is left behind, you go further. What happens actually is that the space-time gets curved to tinier and tinier scales, and it can, depending for how supermassive black hole it is, it could reach the limits of 10 to the power minus 33 centimeters. I mean, inside the potential energy well. So that would be a special scale. Actually, what happens, we know of three fundamental constants of nature, h cross, c, and Newton's constant, g. Out of these three, you can construct three new constants, which are called Planckian mass, Planckian time, and Planckian length. Okay. So you see, you will find that the physics near the Planckian scales starts changing, and classical theories cannot explain it beyond the Planckian scales, or even little bit below the Planckian scales. You see, the classical theories stop working, or showing that there is a breakdown of classical theory. You see, so this is the the understanding from the point of view of the potential energy. And you see, when the size of a quantum particle of mass m, or its Compton wavelength HYMC reaches the value of its Schwarzschild radius of that particle, then you would need a theory of quantum gravity. Classical theories would not explain the situation. So I think that might convince us that yes, we need something beyond the general relativity, which is just a classical theory. Another very famous example I could quote is the black hole information paradox. So black holes are also not eternal, howsoever massive or supermassive they may be, howsoever big or heavy they may be, but eventually they decay away. And so through thermal radiation, Stephen Hawking's well-known birth. So eventually they decay away. And the information as to what once formed a black hole might get lost in the process. This was the main worry of Mr. Hawking. So, because that would lead to the breakdown of unitarity of quantum mechanics or inconsistency with the unitarity of quantum mechanics. So, quantum mechanics has to be unitary, and therefore you have to modify your quantum laws. And that is what I'm trying to present my thoughts on my understanding, views on this point. So we are convinced that you need something beyond the classical theories to explain many further things. So I think with this much background, I think we are ready to now explore what should be a quantum theory of gravity. How could I go about it? Well, that's a very good question. I know of standard model, it's very successful, and it's a gauge theory, and it has local symmetry, very good, beautiful, but it doesn't have gravity. So what I do, I have to introduce somehow gravity into this. Remember that standard model or conventional quantum field theory uses flat space-time manifold. So you can't have gravity in a flat space-time manifold. What you do, I would like my space-time manifold to be curved so that gravity comes into the picture. So I would replace my metric tensor by a the coordinates that span the space-time manifold. And then the theory becomes, I would require it to be invariant under general coordinate transformations, which vary from point to point in the space-time manifold. And because that would give me the principle of general covariance. So that is very holy concept for us. Fine. Other thing that I would do is I would introduce supersymmetry into the theory. The moment I do that, I obtain a new modified theory, which is supersymmetric standard model. It's a supersymmetric field theory. What is a supersymmetric field theory? It must satisfy the super Poincare algebra, and it must satisfy supersymmetric transformations. Well, so we satisfy that. Now, in the supersymmetric standard model, we get the particle spectrum of the theory gets doubled because you have a super partner for each and every particle. Because supersymmetry rotates bosons into fermions and fermions into bosons. So you have, and you can mathematically prove that number of bosons is identically the same as the number of fermions in a supersymmetric field theory. Very good. But then this supersymmetry that is present in supersymmetric standard model is a global or rigid supersymmetry. It's not local. So it does not depend on the space-time coordinates x mu. And so simultaneously you introduce supersymmetry into the theory and you make your metric tensor as curved, non-flat. Very good. Then that starts solving our problem. We are now on the right ladder. We can climb it very well. Very good. So now I'm trying to make my theory local. Very good. Like the standard model, and I'm introducing gravity. So you see, as soon as you make the metric non-flat or curved or function of x mu, then you have already introduced gravity. But we have to do it correctly. So what we do, you see, this theory has a gauge, global gauge symmetry, global symmetry. We have to make it local. So there is a standard procedure for doing it. It's called Neuveu's procedure for constructing local symmetries out of global symmetries. And what you do is, for example, take complex scalar field or Dirac field and replace your derivative by a covariant derivative. Introduce a gauge field into the theory. And for quantum electrodynamics, it's the U1 gauge field, photon field, A mu. Now, I would do the same here for my supersymmetric field theory. As a result, what I will have to do is, I will have to do it through a super covariant derivative. I will have to introduce a super gauge field. This super gauge field is a field which turns out to be a spin 3.5 field. So it's fermionic, not bosonic. Before this, you have encountered only and only bosonic, like photon, gluons, W plus minus. They were all bosons. Okay. But now it's a vector valued spinner or spinner valued vector. And it's a spin 3.5 particle. But it's a beautiful particle. Gravity, I love it. So, I have introduced gravity, but then remember that when we introduce a new field, the gravitino field, then it must be dynamical so that it can interact and talk around with others. Otherwise, it's of no use. If I think I cannot talk to you people, then it's of no use. You see, so you have to be able to talk around. So you have to introduce a kinetic energy term for this gauge field, which is given by a action called as Rarita-Swinger action. It was written down in 1941, 80 years ago, by William Rarita and Julian Swinger, exactly 1941. So 80 years ago. See, so very landmark things have been happening.
It's 4 o'clock.
But even you see the graviton, because we have introduced local symmetry, and G mu nu itself becomes a gravitational field. So we have graviton, but we have to make it dynamical. So we have to introduce its kinetic energy, and that is what you do in terms of the Hilbert-Einstein action. Wonderful. Once you have done all these steps, then you have cooked up your theory of quantum gravity. At the moment, let me not call it theory of quantum gravity. Let me call it a theory, new theory, which I would call as a supergravity theory. So supergravity theory is different than the supersymmetry theory in the sense the supersymmetry theory had only global symmetry. Supergravity has local symmetry. The earlier theory, supersymmetric standard model, did not have gravity at all in it, but now this has gravity by construction. As I have just told you, elaborated the main steps. This I have done consciously for my younger friends. This is how you do it. Now, you see, you can, how many supersymmetry you want to have? 1, 2, 4, 8, and how many? What happens? So, there is a supercharge corresponding to each supersymmetry. If I have introduced only one supersymmetry, I have one supercharge. It would annihilate my gluon state with spin plus 2 only once, and it will give me a state, new state, the gravity node, which is spin reduced by 1/2. Okay. But supposing I have 2 supersymmetries, then I will have 2 supercharges. Each one of them can annihilate the graviton state with a spin plus 2 and can give me 2 gravity. But the 2 can annihilate it simultaneously also to give me a photon state with spin just 1 plus 1. So I have now graviton with spin plus 2, 2 gravity node with spin plus 3/2, and 1 photon-like vector particle with spin plus 1. Now, let me remind you that this is the dream theory of Mr. Einstein. Had he been present today, he would have been very happy to hear about it. But during his times, all these things had not gone that far. Because n equal to 2 supergravity theory unifies gravitational interaction with electromagnetic interaction. As I told you in the particle spectrum, you have 1 graviton, 2 gravitinos, 1 photon. So you have gravity, you have electromagnetic interaction. This is what Mr. Einstein wanted to do or achieve. Anyway, now we have good luck. And now, if I have any...
Professor?
Yes?
Would be okay?
About 15 minutes?
Okay, 10 minutes?
15 minutes? Okay, 15 I will do. In 15 minutes I will do. Now, so if I have 4 supersymmetries, then I will have 4 supercharges. If I have 8 supersymmetries, then I would be very happy. Now, I would have 8 supercharges. I would be able to annihilate my graviton state with a spin plus 2 8 different times, and thereby obtaining different states. Let me enumerate them. graviton with spin plus 2, then gravitino with spin plus 3.5, then vector particles with spin plus 1, then fermions with spin 1.5 plus 1.5, then scalars. So you can calculate, and there you can go up to the other end. So then with equal number of particles with opposite helicity. Okay. So even you will have a graviton with helicity minus 2, 8 gravitinos with spin minus 3.5, and 28 vector particles with spin minus 1. How do you calculate this? 1, 8, 28, 56, and 70 scalars, like the unique Higgs scalar of a standard model. Now you have 70 Higgs scalars, 70 God particles, okay, with spin 0. How do you obtain it? You multiplicity you get by 8C0, 8C1, 8C2, up to 8C8. Okay, and you annihilate this state. This actually can be understood in terms of Pauli-Lubansky vector and the Lorentz translation vector premium. So from here you calculate the helicity of a state, that this W mu, the Pauli-Lubansky vector, is proportional to the dot product of P and W. From there you calculate the helicity of a state. Okay, so this much for this. Now let me tell you some good aspects of this. Why are we doing all this? What is the advantage? You see, when I make my theory from n equal to 0 supersymmetry, which is a standard model, to n equal to 1 supersymmetry or supergravity, what I obtain? You calculate the self-energy of X, it would be convergent in supersymmetric standard model. It was divergent earlier. And so on. Now let me consider an example, photon-photon scattering going to photon-photon. Let me consider fourth order one-loop diagram. Let me calculate them in n equal to 1 supergravity and n equal to 2 supergravity. You will find that the results in n equal to 1 supergravity are divergent, but in n equal to 2 supergravity, they are convergent. The divergences cancel out exactly. So supergravity theory is finite, order by order in perturbation theory. This is the advantage of the supergravity theory. And because it's finite, order by order, therefore it has predictive power. In fact, all these various processes that you can think of in ordinary standard model, they could all be calculated they are calculable in supergravity theory. The only disadvantage is that it is very difficult to confront them with experiments because these numbers are too tiny. So you need a smart, brilliant younger generation that can think of alternative experimentation, that who can detect a gravitino in the lab or a graviton in the lab. One friend of mine at Groningen is doing a tabletop experiment to discover experimentally a graviton. So I told him, why not also look for gravitino? Because if you can find gravitino, you confirm several things. You confirm supersymmetry, you confirm supergravity, and you confirm theory of quantum gravity. Everything in one go. Well, now let me go a little bit beyond in my last 10 minutes. That you see, there are the Newton's laws and Coulomb law, both are singular at r equal to 0, and you have Heisenberg uncertainty principle, delta x equal to h cross by delta p. So what happens in the conventional field theory, in the Feynman diagram calculations, delta x can go all the way up to 0 and delta p can go all the way up to infinity. This leads to infinity. At the source is the Coulomb law of force, and this is being renormalized. Okay, and then you get rid of them through renormalization, where the uncertainty principle comes to your rescue to smear out these singularities. Now, what about the singularities caused due to Newton's law of gravitation? This is also singular at r equal to 0. In order to take care of this, what we do is we have to modify our uncertainty principle. So delta x is h cross by delta p plus a second term, which is proportional to delta p by h cross times a constant alpha prime, which is the universal Ray's law. The price that we have to pay, the advantage is that now delta x cannot go to 0 all the way. Delta p cannot go to infinity all the way, but there is a minimum distance scale set by this modified uncertainty principle, and which is 10 to the power minus 33 centimeters, which is the length scale of string theory. The price you have to pay, so you don't get these infinities or divergences because of that, but the price you have to pay is you have to replace your zero-dimensional particles and fields by one-dimensional objects that are called strings. There could be open strings, there could be closed strings, and these strings have tension, they could vibrate, their vibrational modes could be identified. The different particles, you can consider the action, obtain the equations of motion as usual, and what happens? These equations of motion of string theory, they have, remember that supergravity theory is a theory for zero-dimensional particles. And the theory that I am now talking is a theory for one-dimensional objects. Okay, so the equations of motion that you obtain in superstring theory, they have solutions with 4 large flat dimensions and 6 small curled up dimensions. I pick up one of them and make it a circle, and I go to the limit. The radius of this circle goes to 0. This is how I compactify the extra dimensions, and they can be compactified into a tiny space of the order of 10 to the power minus 33 centimeters. And so you don't have to worry about those extra dimensions. Now, one can proceed. You can have bosonic strings or you can have superstrings. So what happens when a string moves around in the space-time manifold? It sweeps out a trajectory called as the bird seat. It could be a seat, it could be a tube. So now just think, in ordinary field theory, we have, when 3 bird lines meet, we have a vertex, interaction vertex, and this is zero-dimensional. And that was the cause of the divergences, the zero-dimensional vertices of field theory. But now, one seat goes into 2 seats, or one tube goes into 2 tubes, or vice versa. So the interaction vertex, zero-dimensional interaction vertex, has got replaced by a vertex spread in space-time manifold. And therefore, the theory will have to be, by construction, it would be a super renormalizable theory. There would be no divergences whatsoever. Even if some divergences, rigorously speaking, were left in supergravity theory because of the singularity of the Coulomb of the Newton's law of gravitation at r equal to 0, then they would not appear anymore in string theory, because now the vertex is no longer zero-dimensional. It's spread into space-time manifold. So that is the beauty. Now, supposing I cut the story, I make the story short. So if you construct the mass spectrum of this theory, let me skip some details, then what you find that the ground state of a bosonic string theory, for example, is a tachyon, and ground state of even the closed string is also a tachyon with negative mass squared, which means imaginary mass. So it's unphysical. But first excited state of open string theory is a photon-like object with 24 transverse components, because bosonic string theory is defined consistently in 26 dimensions, but superstring is consistently defined in 10 dimensions. So no problem. In superstring theory, this photon-like object would have 8 transverse components. And the closed string theory would have graviton in the mass spectrum in the first excited state, along with some other fields like two-form gauge field, antisymmetric gauge field, and the dilaton scalar, and so on. So if you construct the mass spectrum, let us say, of a fermionic string theory, so you have to introduce both bosonic and fermionic. Without fermions, matter will not be there, so it would be unrealistic. So therefore, you have to have superstring, because you need to have matter also into account. So now then, in the so-called Raymond sector, the mass spectrum consists of space-time fermions given by 10-dimensional Dirac equation, and in the Neuveu Schwarz sector, they are given by the 10-dimensional Klein-Gordon equations. Here you can obtain the mass spectrum would give you space-time bosons. You can, in fact, it's hard work, but brave souls are working on it. So the mass spectrum for massless particles of the superstring theory tallies exactly with what you have in supergravity theory. In addition to that, you have an infinite tower of massive modes in the energy range of the Planckian energy range. You see? So this is fine. The present day accelerators cannot detect them because they are in the Planckian range. But then this is the correct way to do it, and there would be no divergence. In string theory, there are several achievements like black hole information paradox, black hole entropy. All these things are very well acted. Many of these issues that were unresolved prior to this get resolved now, and because I am mentioning superstring theory, I must not forget, I must emphasize that supergravity theory, in particular 8 equal to 8 supergravity theory, could be an ideal candidate for a theory of quantum gravity. Here, one graviton gets replaced by a kind of a superparticle which has various other states as its different polarization states. So a graviton with a spin plus 2, gravitinos with a spin plus 3.5, and so on, all the way up to graviton with a spin minus 2, gravitinos with a spin minus 3, and the intermediate, all these particles, as I told you. So, and to my best guess, n equal to 8 supergravity theory might turn out to be completely free of all divergences. You see, in supergravity theory, divergences cancel at the S matrix level. In ordinary field theory, they cancel because of the renormalization procedure. You get rid of them through renormalization. So we must not forget the supergravity, n equal to 8 supergravity. If you go beyond that n equal to 8, then you will end up postulating particles with a spin higher than plus 2. Okay, so we avoid that for the time being. It will take decades and so on. Anyway, so superstring theory could be the correct theory of quantum gravity. It is obviously a theory of one-dimensional objects. Supergravity is a theory of zero-dimensional objects. Now, so supergravity theory could be the meaningful low-energy limit of the superstring theory. So you have to arrive from superstring theory, you have to arrive at some meaningful low-energy compactifications of the superstring theory to be able to make contact with the experimental observations. We have to be, you see, standard model on the one hand or supersymmetric standard model on the one hand can make contacts with experiments. Supergravity could make contacts with experiments if you were smart enough. You invent some new experiments. If you depend on LHC and other labs, Fermi labs and so on, then it might take, I don't know, longer and longer, much longer times. But if you come up with some ideas like the people are doing at Groningen, some tabletop experiments, some alternative experimentation, which I think the younger generation must look into. You must try to experimentally discover graviton and gravity. You see, if you discover only graviton, you have not yet verified supersymmetry. If you discover gravity, you have verified supersymmetry, you have verified supergravity, you have verified the possible candidate theory of quantum gravity that explains physics extremely well. It's calculable. You can calculate all the things like electron going to electron, or electron going to a pair of photons through various Feynman diagram. But now, always the contents of the model are always important. How many particles are there? You have to make use of all of them using through some conservation laws and so on. You see, you have to follow the same procedure. You have to do particle physics of supergravity theory. And so supergravity theory is a theory of quantum gravity. Below the Planckian scales, superstring theory is a theory of quantum gravity at the Planckian scales and above the Planckian scales. And standard model or supersymmetric standard model is a theory which can make directly contacts with experiments, and supergravity is in between. You have to make some meaningful reductions of superstring theory with via supergravity all the way up to supersymmetric standard model or standard model, the way you prefer. There are various routes that you can take. So I have tried to explore various concepts involved in the process from the theory of point of view as well as from the point of view of experiments. And you see, all these experimentation these days, they cannot work without a good knowledge of computer science and computers. So science and technology goes hand in hand with science. So you should not think that the talk that I'm presenting, the things that I'm talking are relevant to theoretical physicists or to experimenters. No, they are equally relevant. You see the LHC, the Large Hadron Collider, thousands of brilliant engineers of all kinds and computer engineers of all kinds, they are working on it. When you construct the image of a black hole through this array of, event horizon telescope, through these 8 telescopes spread across the world, you see people like me sitting and doing some calculations on page and paper with pencil or pen. No, by no means. They are brilliant people working with. You can develop computer codes for calculating these Feynman diagrams, like people have done it for QCD or electroweak theory or QED. If you go to textbooks of field theory, you realize that even for calculation of anomalous magnetic moment of an electron, you need 72 Feynman diagrams to calculate it, and experimentally it tallies well. So right from the times of my gurus in particle physics, in field theory, these things were calculable. Like my teacher, Professor Ashok Mitra, he was able to do many of these things just by hand on a piece of paper, you see. So everything goes hand in hand. Mathematics on the one hand, concepts on the one hand. You have to closely understand and connect. Unless you know the physics meaning of mathematics, unless you know the mathematics of physical concepts, you cannot do anything. I'm a great fan of David Hilbert, who used to say his very famous quote that unless whatever complicated things you may be doing, unless you can explain your things in simple language to the next person whom you meet on the street, it's of no use to do complicated. You ought to be able. He was a mathematician par excellence, working at the University of Groningen, the city of Nobel laureates in the 1920s and 30s. There are many buildings belonging to different Nobel laureates. David Hilbert, Einstein always used to look forward. In fact, the covariant, the Einstein equation in the covariant form was first written down by David Hilbert. If you go into the literature and dig it out, the history, and he wrote it on a postcard, sent it to Einstein, who had visited him 3 times, 4 times earlier. You see, so these were the great souls like Einstein, like Hilbert, like Grossman, these people, you see. And people have gone hand in hand with the experimentation, achieving all these success. All theory, I'm just concluding in 1 or 2 minutes.
Okay, thanks.
I'm just concluding. I'm at the conclusion, in fact, already. So you see, nothing goes in isolation. All of you, I would like to motivate all the younger people, and you have to work out your route through whatever you know, not through whatever I know. You develop your knowledge that you have in your own way and try to catch these ideas from all sides and try to see how you can handle it. That is why my friend Professor Müller-Christen in Kaiserslautern used to tell me, if you want to go to string theory, this is some decades ago, he used to tell me, if you want to do string theory, well, yes, you have to find your own way through whatever you know. And then there was Gyan Maharana from Odisha, my great friend. He turned up at Kaiserslautern. I told him, why don't you tell me some basics about this? How do I start? So you see, Gyan Maharana was a good motivator to me, and he could explain many basic things. So you have ज्ञान का भंडार है आपके पास उड़ीसा में, आप लोग इसका यूज करिए. लंबोदर जी हैं, बड़े विद्वान हैं, और वहाँ पर इतने विद्वान लोग हैं आपके उड़ीसा में. I like to wish you all the best. Make good use of. There is one young boy called Vikas Acharya from somewhere from Odisha. I have never met him, but he keeps in touch with me. He's just a graduate student. Indian language graduate, undergraduate. Very bright boy. I had sent him this link, but I don't know if he could join or not. Anyway, what I want to say, flowers blossom even in the grass, even on the big trees. You have to develop your own, and you have to make it blossom wherever you are, in whichever field you are, whether engineering or science or math. So I wish you all the best. I conclude my talk here on a positive hope, on a positive note, that we are very much around the corner in understanding the candidate theory of quantum gravity. thank you all very, very much for bearing me for such a long time. Thank you all very much. All the best.
Thank you so much, Professor Kulshreshtha, for your inspiring talk on so many super things. We have a proverb in Odia.
Yes.
Ruchu naruchu kha pita, buju nabuju sunu gita,
I see.
poda gita.
And what it means?
So you're all supersymmetry, superstring, supergravity. They are all, in fact, invitations for the young minds
Yes.
to actually engage in those kind of pursuits as they go on ahead in their life.
I like to
anyway,
add one line. Lambodarji, I like to add one line for younger people. I want to tell that Professor Lambodarji is one of my gurus. He taught me the most useful and best formulae of the life. Once we were together in some selection committee in Raurkela, and younger people were coming and saying
it's sufficient.
No. They were saying that they have been visitors at IOP, at Bangalore, at Tata Institute, and in the absence of everybody, Lambodarji told me, Kulshreshtha, aren't we all visitors on earth?
Yes,
I like to convey this message to all my younger people. This is Professor Lambodarji is the original author of this idea. Please try to understand this. We are a visitor on earth.
Okay, thank you so much. Yes, any question from the young people? You can ask him. Yes. No questions. I have one simple question just to know from you.
Yes.
You said that supersymmetric standard model is okay with experiment. Are there experimental proofs or confirmation of supersymmetric standard model?
Let me. It's a very nice question. Let me remind you about the work of one of my great friends, Professor Stan Brodsky at Stanford University.
Brodsky
Center. So he has some papers on supersymmetry in hadronic physics, in baryonic physics, in quark models. You see, so those they are useful for direct contact with experiments. You see. So
but do you have experimental confirmation on any of these?
Not yet. But it could be quite close. You see, you don't have to invent a supersymmetric particle at.
That's good.
But you can verify some of these processes. In particular, look for the work of Stan Brodsky, where he talks about supersymmetric QCD, supersymmetric baryons, and hadron physics in terms of.
Professor. In fact, the best way is to actually see where the grand unification meets, because with supersymmetry, the grand unification is actually a much better point than without supersymmetry.
Yes, very good. Yeah. So we fully agree. So standard model, we have assumed that grand unification has already been achieved within the framework of standard model. So it is assumed.
But we have no experimental.
I have not kept track of various experimental findings of standard model, but I think there are many things. But obviously, nothing confirms supersymmetry in the first place, for sure. But you have to remember that this is a theory in flat space-time manifold, not in curved space-time manifold. So gravity would certainly not be there at all. Gravity for the first time appears only in supergravity theory, not in supersymmetric standard model. You see, supersymmetric standard model is.
I understand. Yes.
That is also defined in flat space-time. But in flat space-time, you can study this supersymmetry in hadronic physics, for example. That can confront experiment.
Okay. Thank you so much.
If you like, I will send you in email some of the work of Stan Brodsky, which he gave me for highlighting to the people who are curious to know how supersymmetry could go in experiments.
Okay, thank you. Thank you so much. And we are really grateful that you accepted so gladly our invitation and you have made this memorial talk really memorable. Thank you so much.
I would have been more happy had I really come there. I personally apologize. And I do look forward to, I take words from Professor Durga Prasad ji he has told me there would be other opportunities for me to come again.
Okay, thank you so much. Thank you.
I love
All
this
the
place,
best.
Odisha. Thank you. Thank you.